We're gathered for final presentations of Fall 2012 16861. First up, for visual closed estimation.
All right, well, we are the Visual Closed Estimation Group. I'm Chris Cunningham.
Megan Downey.
Sandy Miller.
So, the motivation for visual closed estimation is the discovery of ice and satellites on the moon has created sites of interest and destinations for a rover that it would need to know where it is in order to get to. For longer traverses, visual closed estimation is an absolute localization method. It is not susceptible to drift like visual odometry or other methods. Also, in the event of a loss of communication, the rover would be able to navigate autonomously, knowing where it was. From overhead imagery, since GPS is not available, we're able to use this method to localize the rover. Another motivation is that the NASA Resolve payload requires 2-meter accuracy, so we would like to localize within 2 meters. Visual closed estimation was shown to be successful in simulation, and our project was to set out to show that it worked through field testing.
So our initial approach involved capturing the images from a pair of stereo cameras, taking those images and transforming them into a 3D point cloud that could then be projected upwards and be matched with overhead imagery. For this purpose, we were using a Prosilka GC1290 camera, which is a gigabit Ethernet camera, and we were accessing it through the robot operating system. Our field test setup was at Robot City. The location was Robot City. We had 2 field tests and 4 test sites per field test. Each test site, we captured 1 set of data, and that set of data was 8 pairs of stereo images at 45-degree increments in a clockwise direction. Since there was no pan tilt device available, we manually rotated the camera setup on a tripod. As shown here, our initial results demonstrated some limitations with stereo vision. Specifically, you can see the left and right images above and the disparity map produced by those images below. This is the best disparity map we were able to produce by tuning the stereo parameters for our stereo block matching algorithm. Shown on the other side is the actual 3D point cloud that was produced, and as you can see, it's very sparse. It's a full colorized 3D point cloud. Several alternate stereo algorithms were evaluated, including stereo block matching under OpenCV, semi-global block matching, variational matching, a separate Zipnik-Kanade cooperative stereo algorithm, and stereo block matching under MATLAB. As you can see, multiple implementations were tested on multiple implementations of the same algorithm. All of them were tuned and verified with test image sets, such as the Tsukaba image set. Of course, these are mostly indoor data sets, and they were verified to work. However, they did not work very well with our stereo imagery. All of the point clouds generated were too sparse to match the overhead imagery.
So the next approach that we tried was LiDAR scans using a Faro. Directly obtain the colorized point cloud and use GPS to verify ground truth. Various sizes of templates were generated, matched to map at various resolutions. The preliminary field test was performed at Robot City as a proof of concept to ensure that the Faro would work before doing more extensive testing. 5 test sites were taken. 2 of those were determined to be invalid due to construction, and it was found that 2 out of 3 of the test sites were validated. And you can see the matching in the pictures here.
So for our more extensive field test, we also used Robot City. We had considered other locations that were more moon-like environments. However, current overhead imagery is not available, and that's a prerequisite for our algorithm to work. We took 20 test sites. As you can see here, 9 was actually thrown out because of vegetation. In this time, we used a very accurate GPS and used those GPS readings to verify our method. For each of the 20 templates, we constructed, for each of the 20 scans, we constructed overhead projection templates at different sizes, 100 square meters, and so forth. We also constructed them at different resolutions, 0.25 meters per pixel, 0.5 meters per pixel, and 0.2 meters per pixel, and we scaled the overhead maps that we had accordingly. We derived a transformation from GPS coordinates to our map coordinates to be able to correlate the test sites, the GPS readings of the test sites that we took with the matched locations. And then we selected a 100 by 100 square meter or 100 by 100 meter region from the larger map because testing on the entire map is just too computationally complex and takes too long. And then we ran our template matching algorithm. So here are field test results. Out of the 20, 16 were in one way or another proven to or matched with an average matching of 2.57 meters, which is approximately within the margin of error for the GPS anyway. Matches per template size and density are seen here, and it's clear that the bigger you get with fewer meters per pixel and bigger template sizes in meters, you get better matches. This is the smaller images, and the lower right are the larger ones where you can see we had 15 matches in that one versus 2 in this one. So what we did was we validated that the absolute localization algorithm works well. It is not perfect. Larger template sizes and fewer meters per pixel produce better results by allowing for finer detail. But this also brings into account a trade-off between reliability and computational complexity. It's a very expensive algorithm, and the bigger your template size and the bigger your map size, it takes much longer to compute. We also found some limitations of this algorithm, which are lighting conditions. The templates must be rotationally aligned very closely to the map, and we need a dense point cloud, and the stereo was just not able to do that. So in future work, we would implement this using a LiDAR and camera setup instead of just the Faro scanner, which is not viable for the moon. We would test in a more lunar-relevant terrestrial environment. We would take overhead imagery for the same day, which is things we did not have access to this time, and investigate optimizations for the template matching with transparency. There are optimizations that exist, but when you include the transparency, those are rendered invalid. And as you can see here, the current computational complexity is the template height times width times the map height times width, and so it's essentially quadratic and very expensive. We would also do further testing on map size for how well it can match, and investigate other methods for overhead projection using stereo and stereo LiDAR, and finally implement it with a Kalman filter to enable continuous localization. And we'd like to acknowledge these people for helping us with our project. Otherwise, we would not have been able to do this.